Chapter 12: The Future of Data Systems. If a thing be ordained to another as to its end, its last end cannot consist in the preservation of its being. Hence a captain does not intend as a last end the preservation of the ship entrusted to him, since a ship is ordained to something else as its end, viz. To navigation, often quoted as, if the highest aim of a captain was to preserve his ship, he would keep it in port forever. St. Thomas Aquinas, Summa Theologica 1265-1274. So far, this book has been mostly about describing things as they are at present. In this final chapter, we will shift our perspective toward the future and discuss how things should be. I will propose some ideas and approaches that, I believe, may fundamentally improve the ways we design and build applications. Opinions and speculation about the future are of course subjective, and so I will use the first person in this chapter when writing about my personal opinions. You are welcome to disagree with them and form your own opinions, but I hope that the ideas in this chapter will at least be a starting point for a productive discussion and bring some clarity to concepts that are often confused. The goal of this book was outlined in Chapter 1, to explore how to create applications and systems that are reliable, scalable, and maintainable. These themes have run through all of the chapters. For example, we discussed many fault tolerance algorithms that help improve reliability, partitioning to improve scalability, and mechanisms for evolution and abstraction that improve maintainability. In this chapter we will bring all of these ideas together and build on them to envisage the future. Our goal is to discover how to design applications that are better than the ones of today, robust, correct, evolvable, and ultimately beneficial to humanity. Data integration. A recurring theme in this book has been that for any given problem, there are several solutions, all of which have different pros, cons, and trade-offs. For example, when discussing storage engines in Chapter 3, we saw log-structured storage, B-trees, and column-oriented storage. When discussing replication in Chapter 5, we saw single-leader, multi-leader, and leaderless approaches. If you have a problem such as I want to store some data and look it up again later, there is no one right solution, but many different approaches that are each appropriate in different circumstances. A software implementation typically has to pick one particular approach. It's hard enough to get one code path robust, and performing well. Trying to do everything in one piece of software almost guarantees that the implementation will be poor. Thus, the most appropriate choice of software tool also depends on the circumstances. Every piece of software, even a so-called general-purpose database, is designed for a particular usage pattern. Faced with this profusion of alternatives, the first challenge is then to figure out the mapping between the software products and the circumstances in which they are a good fit. Vendors are understandably reluctant to tell you about the kinds of workloads for which their software is poorly suited, but hopefully the previous chapters have equipped you with some questions to ask in order to read between the lines and better understand the trade-offs. However, even if you perfectly understand the mapping between tools and circumstances for their use, there is another challenge. In complex applications, data is often used in several different ways. There is unlikely to be one piece of software that is suitable for all the different circumstances in which the data is used, so you inevitably end up having to cobble together several different pieces of software in order to provide your application's functionality. Combining specialized tools by deriving data. For example, it is common to need to integrate an OLTP database with a full-text search index in order to handle queries for arbitrary keywords. Although some databases such as PostgreSQL include a full-text indexing feature, which can be sufficient for simple applications, more sophisticated search facilities require specialist information retrieval tools. Conversely, search indexes are generally not very suitable as a durable system of record, and so many applications need to combine two different tools in order to satisfy all of the requirements. We touched on the issue of integrating data systems and keeping systems in sync on page 452. As the number of different representations of the data increases, the integration problem becomes harder. Besides the database and the search index, perhaps you need to keep copies of the data in analytics systems, data warehouses, or batch and stream processing systems, maintain caches or denormalized versions of objects that were derived from the original data, pass the data through machine learning, classification, ranking, or recommendation systems, or send notifications based on changes to the data. Surprisingly often I see software engineers make statements like, in my experience, 99% of people only need X or don't need X for various values of X. I think that such statements say more about the experience of the speaker than about the actual usefulness of a technology. The range of different things you might want to do with data is dizzyingly wide. What one person considers to be an obscure and pointless feature may well be the central requirement for someone else. The need for data integration often only becomes apparent if you zoom out and consider the data flows across an entire organization. When copies of the same data need to be maintained in several storage systems in order to satisfy different access patterns, you need to be very clear about the inputs and outputs. Where is data written first? And which representations are derived from which sources? How do you get data into all the right places, in the right formats? For example, you might arrange for data to first be written to a system of record database, capturing the changes made to the database. See Change Data Capture on page 454, and then applying the changes to the search index in the same order. If Change Data Capture, CDC, is the only way of updating the index, you can be confident that the index is entirely derived from the system of record, and therefore consistent with it barring bugs in the software. Writing to the database is the only way of supplying new input into the system. Allowing the application to directly write to both the search index and the database introduces the problem shown in Figure 11-4, in which two clients concurrently send conflicting writes, and the two storage systems process them in a different order. In this case, neither the database nor the search index is in charge of determining the order of writes, and so they may make contradictory decisions and become permanently inconsistent with each other. If it is possible for you to funnel all user input through a single system that decides on an ordering for all writes, it becomes much easier to derive other representations of the data by processing the writes in the same order. This is an application of the state machine replication approach that we saw in Total Order Broadcast on page 348. Whether you use Change Data Capture or an event sourcing log is less important than simply the principle of deciding on a total order. Updating a derived data system based on an event log can often be made deterministic and idempotent. See idempotence on page 478, making it quite easy to recover from faults. Derived data versus distributed transactions. The classic approach for keeping different data systems consistent with each other involves distributed transactions, as discussed in Atomic Commit and Two-Phase Commit 2PC on page 354. How does the approach of using derived data systems fare in comparison to distributed transactions? At an abstract level, they achieve a similar goal by different means. Distributed transactions decide on an ordering of writes by using locks for mutual exclusion. See two-phase locking 2PL on page 257, while CDC and event sourcing use a log for ordering. Distributed transactions use atomic commit to ensure that changes take effect exactly once, while log-based systems are often based on deterministic retry and idempotence. The biggest difference is that transaction systems usually provide linearizability. See linearizability on page 324, which implies useful guarantees such as reading your own rights. See reading your own rights on page 162. On the other hand, derived data systems are often updated asynchronously, and so they do not by default offer the same timing guarantees. Within limited environments that are willing to pay the cost of distributed transactions, they have been used successfully. However, I think that XA has poor fault tolerance and performance characteristics. See distributed transactions in practice on page 360, which severely limit its usefulness. I believe that it might be possible to create a better protocol for distributed transactions, but getting such a protocol widely adopted and integrated with existing tools would be challenging and unlikely to happen soon. In the absence of widespread support for a good distributed transaction protocol, I believe that log-based derived data is the most promising approach for integrating different data systems. However, guarantees such as reading your own rights are useful, and I don't think that it is productive to tell everyone eventual consistency is inevitable. Suck it up and learn to deal with it, at least not without good guidance on how to deal with it. In aiming for correctness on page 515, we will discuss some approaches for implementing stronger guarantees on top of asynchronously derived systems, and work toward a middle ground between distributed transactions and asynchronous, log-based systems. With systems that are small enough, constructing a totally ordered event log is entirely feasible, as demonstrated by the popularity of databases with single-leader replication, which construct precisely such a log. However, as systems are scaled toward bigger and more complex workloads, limitations begin to emerge. In most cases, constructing a totally ordered log requires all events to pass through a single leader node that decides on the ordering. If the throughput of events is greater than a single machine can handle, You need to partition it across multiple machines. See partitioned logs on page 446. The order of events in two different partitions is then ambiguous. If the servers are spread across multiple geographically distributed data centers, for example, in order to tolerate an entire data center going offline, you typically have a separate leader in each data center, because network delays make synchronous cross-data center coordination inefficient. See multi-leader replication on page 168. This implies an undefined ordering of events that originate in two different data centers. When applications are deployed as microservices, see data flow through services. REST and RPC on page 131. A common design choice is to deploy each service and its durable state as an independent unit, with no durable state shared between services. When two events originate in different services, there is no defined order for those events. Some applications maintain client-side state that is updated immediately on user input without waiting for confirmation from a server, and even continue to work offline. See clients with offline operation on page 170. With such applications, clients and servers are very likely to see events in different orders. In formal terms, deciding on a total order of events is known as total order broadcast, which is equivalent to consensus. See consensus algorithms and total order broadcast on page 366. Most consensus algorithms are designed for situations in which the throughput of a single node is sufficient to process the entire stream of events, and these algorithms do not provide a mechanism for multiple nodes to share the work of ordering the events. It is still an open research problem to design consensus algorithms that can scale beyond the throughput of a single node and that work well in a geographically distributed setting. In cases where there is no causal link between events, the lack of a total order is not a big problem, since concurrent events can be ordered arbitrarily. Some other cases are easy to handle. For example, when there are multiple updates of the same object, they can be totally ordered by routing all updates for a particular object ID to the same log partition. However, causal dependencies sometimes arise in more subtle ways. See also ordering and causality on page 339. For example, consider a social networking service and two users who were in a relationship but have just broken up. One of the users removes the other as a friend, and then sends a message to their remaining friends complaining about their ex-partner. The user's intention is that their ex-partner should not see the rude message, since the message was sent after the friend status was revoked. However, in a system that stores friendship status in one place and messages in another place, that ordering dependency between the unfriend event and the message send event may be lost. If the causal dependency is not captured, a service that sends notifications about new messages may process the message send event before the unfriend event, and thus incorrectly send a notification to the ex-partner. In this example, the notifications are effectively a join between the messages and the friend list, making it related to the timing issues of joins that we discussed previously. See time dependence of joins on page 475. Unfortunately, there does not seem to be a simple answer to this problem. Starting points include: logical timestamps can provide total ordering without coordination. See sequence number ordering on page 343, so they may help in cases where total order broadcast is not feasible. However, they still require recipients to handle events that are delivered out of order, and they require additional metadata to be passed around. If you can log an event to record the state of the system that the user saw before making a decision, and give that event a unique identifier, then any later events can reference that event identifier in order to record the causal dependency. We will return to this idea in Reads or Events 2 on page 513. Conflict resolution algorithms. See automatic conflict resolution on page 174. Help with processing events that are delivered in an unexpected order. They are useful for maintaining state, but they do not help if actions have external side effects such as sending a notification to a user. Perhaps, over time, patterns for application development will emerge that allow causal dependencies to be captured efficiently and derived state to be maintained correctly, without forcing all events to go through the bottleneck of total order broadcast.